Thank you very much. And I'm so sorry that British Airways canceled my flights so that it was impossible for me to come to London and make it home in time to cook dinner for 9 people at our big festival, Thanksgiving in the US. These are my competing interests. I do not accept any personal payment from any pharma or device company for which I can write a prescription, but I do participate in trials and scientific advisory boards and have some financial interests in biotech companies that are startups that don't have any products. Well, just at the get-go, let me dispel a notion which has haunted us in this field of inflammation for many years, and that is that there's some kind of a competition between inflammation and traditional risk factors, which we've been speaking about today. Let me underscore that inflammation does not supplant or demote any traditional risk factors such as LDL, hypertension, diabetes, but inflammation provides a set of mechanisms that link these traditional risk factors to altered behavior of the artery wall and beckon into the artery wall the unwelcome inflammatory cell visitors that give rise to disease and its complication. Now, many of you have made slides like this. Many of you have slides like this. I'm not going to belabor this issue because it's no longer news that inflammation is part and parcel of atherosclerosis from its very initiation, when we recruit those leukocytes and accumulate foam cells in the arterial intima, through the phase of complication, which is often clinically silent or stable, when we bring smooth muscle cells from the media into the intima, and those that reside in the intima in human arteries will proliferate and secrete extracellular matrix. And of course, what brings the patients to our attention as cardiologists most dramatically are the thrombotic complications of this disease. And my laboratory and many, many others around the world have spent decades unraveling the cellular and molecular mechanisms that lead to each of these steps from the initiation through the progression and ultimate complications of this disease. We spent maybe several decades working out the pathophysiology of plaque rupture, shown here, which is still the dominant cause of acute coronary syndromes. But I think in the current era, as LDL is dropping worldwide due to dietary change and pharmacotherapy, I think that superficial erosion is becoming now more important and accounts for something like 25 to 30% of ACS. And it's interesting that after focusing for many decades on the mononuclear phagocyte as the prime inflammatory cell in atherogenesis and its complications, we've now turned our focus, driven by the data, to the polymorphonuclear leukocyte and have worked on neutrophil extracellular traps, which are on the cutting edge of thrombosis research. So just to say that the field is still in evolution. Now, what are the messengers that mediate the triggering of inflammatory mechanisms and link with risk factors in atherosclerosis? Well, there are protein mediators of inflammation and immunity, such as the cytokines and chemokines. There are lipid mediators, of which there's a large variety, and you've heard a lot about them. And there are also reactive oxygen species. Now, I'm going to focus, because we have only 20 minutes or so for our discussion this afternoon, on the cytokines, because that's where I've spent most of my time. And actually, I'm going to hone in on one particular cytokine for purposes of illustration, interleukin-1, and in particular, the beta isoform of this actually triad of pro-inflammatory mediators. And back in the 1980s, we did some very early work that showed that despite the protests of my immunology colleagues, that human vascular cells could produce these mediators that were named interleukins because they were supposed to only signal between leukocytes. and it was considered very contrarian and controversial at the time, that when we stimulated human endothelial cells or smooth muscle cells, the intrinsic cell types involved in atherosclerosis, when we stimulated them with a pro-inflammatory stimulus, in this case, gram-negative bacterial endotoxin or lipopolysaccharide, we induced the accumulation of a message that encoded interleukin-1 beta. At the time, actually, we thought that LPS was sort of an artificial laboratory stimulus, but now with increasing appreciation of the importance of the microbiome and of epithelial leak in certain conditions, we think that LPS is much more biologically relevant than we had imagined back in the mid-1980s. Now, very soon after that, we discovered that IL-1 can induce its own gene expression, setting up an amplification loop. We did that in endothelial cells, as shown here, in smooth muscle cells, and together with Charles Dinarello, who's really the godfather of interleukin-1 beta, who purified it and cloned it, we showed in human mononuclear phagocytes and in rabbits in vivo that IL-1 can induce its own gene expression. Very soon after that, we found that IL-1 could induce another pro-inflammatory cytokine known as interleukin-6. This is a log-log plot and shows how tremendous the amplification is when we put a drop of IL-1 on human vascular smooth muscle cells, and this also works in endothelial cells. We get out enormous quantities of interleukin-6, which we were already interested in back in the 1980s for reasons that I will explain in a moment. Now, interleukin-1 beta, like many proteins that are pivotal in biological control, is first synthesized as an inactive precursor and requires a limited proteolytic cleavage to gain its biological activity. We were able to localize the enzyme that catalyzes this limited proteolysis, known first as ICE for interleukin-1 beta converting enzyme, now known as the founding member of the caspase family. We were able to localize it in foam cells and human atherosclerotic plaques in the mid-1990s. And in the biochemistry laboratory, we were able to show that stimulating human vascular cells with a pro-inflammatory stimulus that we already knew was operating in human atherosclerosis, in this case, CD154 or CD40 ligand, we were able to coax the processing of the inactive precursor to the active cytokine. And this was dependent on this enzyme. Well, what we didn't know when we were doing those biochemical experiments was that hard at work in Lausanne, Switzerland, the laboratory of the late Jörg Schopp found that caspase-1 is the business end of a supramolecular structure that we now know as the inflammasome, that has outside arms that are danger signal sensors, including sensing danger from atherosclerosis appropriate stimuli, such as cholesterol crystals, that activates the inactive caspase-1, and that can then catalyze the production of active IL-1 beta and its cousin IL-18. So now we have a real biochemical pathway, if you will, with the inflammasome transducing danger signals related to our risk factors, boosting the production of the active pro-inflammatory cytokines that are apical in this signaling pathway. IL-1 then can induce its own gene expression, as I illustrated, causing an amplification loop. IL-1 can then induce enormous amounts of interleukin-6, another amplification loop. And the reason that we were interested in IL-6 way back when was because we already knew that it was the trigger for the acute phase response in the hepatocyte, telling the liver cell, well, tone down your synthesis of housekeeping proteins such as albumin and take some of your substrate and energy and get us prepared to respond to injury. And the acute phase reactants include fibrinogen, the precursor of clots, and plasminogen activator inhibitor, the major blocker of our own fibrinolytic system. Now, these are terrible biomarkers for various reasons, but a very high fidelity biomarker is C-reactive protein, particularly measured with a high sensitivity assay, that allows us to look through the glass darkly at this entire pathway. So I pointed out that the leukocytes are the unwelcome visitors to the artery wall in atherogenesis. And where do they come from? Do they come from recruitment from blood? Yes. Local proliferation in plaques? Yes. Extramedullary hematopoiesis under emergency conditions? Yes. And I'm not going to show you the data, but I would like to focus on something which has been a real explosion of activity in the last year or so, and that is hematopoiesis in the bone marrow. So what are the mechanisms that might accentuate leukophoresis and supply those white cells that we find in the atherosclerotic plaque and that cause much of the havoc in the complication of the disease? Could it be inflammatory signaling in the bone marrow niche, the hematopoietic niche, or could it be clonal hematopoiesis? So I'm going to consider both of those. Let's start with the notion that an atherogenic environment that is created by those risk factors can actually stimulate leukophoresis in the bone marrow. And in experiments that were led by my colleagues, Matthias Nahrendorf and my former postdoctoral fellow, Phil Swirsky, with a very talented team of young investigators, if one takes atherosclerosis-prone mice and gives them a diet enriched in cholesterol and saturated fat, a Western-type diet, and takes the endothelial cells from the bone marrow and sorts them to purify them and does RNA sequencing, among the proteins that are encoded by the RNA that are most elevated include interleukin-6. And if we then go and do the functional experiment where we extinguish interleukin-6 expression in the endothelial cells in a similar kind of experiment, we see, let me just take you over here to the summary data, that there's a decrease in the stem cells that give rise to the leukocytes and decrease in the pro-inflammatory subset of monocytes and a decrease in those neutrophils. So it looks like interleukin-6 in the bone marrow niche, induced by an atherogenic diet, can increase proliferation of leukocyte progenitors in the bone marrow and give rise to those cells that show up in the atherosclerotic plaque. Now, I'd like to also consider another possibility, and that is that somatic acquired mutations may also boost the accumulation of leukocytes. This is a new area that is called clonal hematopoiesis, or clonal hematopoiesis of indeterminate potential, as I'll explain in a bit, CHIP. And it is quite interesting because it unites aging, cancer, and cardiovascular disease. If you'd like to read about it in depth, there are a number of good reviews. This is one that we contributed a few years ago. So with age, hematopoietic stem cells in your bone marrow can acquire somatic mutations. These are not mutations you inherit from your mother or father, but that are acquired during life, hence the aging exposure. And some of these mutations, most of them are silent, but some of them are in known leukemia driver genes. And they can cause the accumulation of these mutant cells in the peripheral blood. And that's a first step on the road to leukemia. Actually, individuals who have 2% of these mutated cells in their bloodstream are indicated as having clonal hematopoiesis of indeterminate potential. Indeterminate potential because most people will never know it. It's sort of like monoclonal gammopathy of unknown significance. Most people will never develop multiple myeloma. Why? Because it requires the acquisition of about 3 mutations in the same clone in leukemia driver genes to become leukemia. So why should we care about it? It's because although the transition to acute leukemia is rather uncommon, on the order of 0.5 to 1% per year, there is a consistent increase in cardiovascular events. And every time you open a journal, there's a new cardiovascular condition that has been associated with CHIP. If we stack up the presence of CHIP with traditional risk factors, it looks pretty potent. Of course, age is the biggest driver. Diabetes, which we've heard a lot about here, is also gives you more than a 2-fold enrichment in risk for cardiovascular disease. But CHIP actually is on the same order or even greater than hypertension or cholesterol. So this is a potent risk factor that was unsuspected just a few years ago. It's only a handful of the known leukemia driver genes that cause most of this. And here is the age curve showing that by the time that you're 70, you have at least a 10% chance of having one of these clones swimming in your bloodstream. So, of course, there are two possibilities, aren't there? One is that we're just counting the rings of growth around the trunk of the tree. And since the mutations accumulate with age, and because the atherosclerosis increases with age, it's true and unrelated. Or could it be that there is a causal relationship between the clones and cardiovascular disease? To confront that conundrum, we did experimental studies in my laboratory in conjunction with the hematology oncology team that has uncovered this link. And we're able to do the usual kind of experiment in mice where we've mimicked the loss of function of some of these genes. And we show indeed that there is an acceleration of atherosclerosis when we've mimicked clonal hematopoiesis in mice. So both inflammatory signaling in the bone marrow niche due to traditional risk factors such as hypercholesterolemia and this new entity of clonal hematopoiesis can drive atherogenesis. So these are based on a lot of mouse experiments, at least the causal experiments. So is it possible that components of the metabolic syndrome actually also drive bone marrow activation in humans? And for that, we have recent data from the PESA study in Madrid in the workers of the Santander Bank, led by Valentin Fuster and Borja Ibanez. And what they were able to show using bone marrow uptake of fluorodeoxyglucose, as shown here in the PA and here in the lateral, that if you stack up different components of the metabolic syndrome, you get increased metabolic activity in the bone marrow. And that's completely concordant with work from the group of Phil and Matthias, and some of which I contributed to in the mouse, showing that these various lifestyle-related risk factors can drive hematopoiesis at the bone marrow level. Well, I would like to now get to clinical translation because it takes me 80 milliseconds to come up with almost 1.8 million hits if I cross inflammation and atherosclerosis in Medline, in Google Scholar. It takes 80 milliseconds to come up with over 300,000 hits for immunology and atherosclerosis. But how do we cross that valley of death? And that's why I focused on IL-1 beta in our earlier conversation, because I've been studying it for decades, as you saw, and it actually provided us with the first example of a specific anti-inflammatory therapy that might alter cardiovascular outcomes. We designed and conducted CANTOS, the canakinumab anti-inflammatory thrombosis outcome study. And you all know the primary endpoint. This was a pre-specified analysis looking at those who responded well to the drug. We just saw a waterfall plot. And if we look at the people who were on the good side of the waterfall plot in CANTOS, there was an over 30% reduction in cardiovascular mortality and in all-cause mortality in this pre-specified sub-analysis. Now, that was a win by neutralizing interleukin-1 beta. What about other anti-inflammatory drugs? Well, Dr. Ridker designed and carried out the cardiovascular inflammation reduction trial using methotrexate, which is an anti-inflammatory intervention that's changed radically the practice of rheumatology. And in this very well-conducted study, he found no benefit in terms of cardiovascular disease. But note, as opposed to CANTOS, where the inflammatory biomarkers decreased, that there was actually no effect on inflammation in the enrolled population in the CERT trial. But fortunately, we have some actionable anti-inflammatory therapies. We have the COLCOT trial in people with recent myocardial infarction treated with colchicine showing a striking decrease in recurrent events. And in patients in the more chronic phase of atherosclerosis in LODOCO2, you see the decrease in events with colchicine. Now, colchicine, of course, has some limitations and may also, like canakinumab, increase susceptibility to infection. So where do we go? Well, colchicine is something we have today, and we need to learn how and when to use it. Inflammasome inhibitors going upstream in that pathway, and then anti-IL-6. Dr. Ricker-Morton, 20 years ago, found that there was a very strong relationship between one's basal IL-6 and future cardiovascular events. And there's very good human genetic evidence supporting causality of interleukin-6 in human atherothrombosis. These are common variants which lead to loss of function of IL-6 signaling, and you have a concordant decrease in C-reactive protein that depends on your genotype and risk of having coronary heart disease. So together with Dr. Ritter and some nephrology colleagues, we've actually looked at a patient population that we struggle with in the clinic because they have very high cardiovascular risk and they don't respond so well to statins. And so we actually tested within CANTOS whether those with chronic kidney disease had more dependence for recurrent events on inflammation or LDL. So here was the hypothesis that we tested. And in 8,000 CANTOS participants without chronic kidney disease, stages 3 through 5, we found that if we compare the extreme quartiles, that there was definitely a relationship between both inflammation, as denoted by the biomarker CRP, and lipids, as shown by LDL. But if we look at the 1,100 participants in CANTOS that had chronic kidney disease, while inflammation still predicts recurrent events, the lipids do not. That has been in line with the evidence supporting the application of neutralizing antibodies for interleukin-6, namely ziltivekimab, in patients with high atherosclerotic risk due to chronic kidney disease. The phase 2 study is called RESCUE. Its design is here. It's a usual ascending dose study. And there was a striking reduction in the primary endpoint of high sensitivity CRP. Now in CANTOS, we saw about a 36% reduction in CRP. Here at the highest dose used in this phase 2 study, we saw over 90% reduction, and it was sustained. So that was the prelude to a phase 3 study that is currently enrolling called ZEUS, that is addressing this unmet need, this particular biologic state where LDL seems less relevant for outcomes and statins do not seem to be as effective, at least in end-stage kidney disease, and where inflammation appears to be more relevant, and where the presence of chronic kidney disease would stay our hand for using colchicine. So where are we? Well, as Winston Churchill said, at a turning point in the Second War. Now, this is not the end. It is not even the beginning of the end, but it is perhaps the end of the beginning. Now, I was asked to talk about the knowns and the unknowns. And in all humility, we're still struggling with how to apply anti-inflammatory therapy in the clinic. Now, when I went with Paul Ridker to Basel to pitch the study that became CANTOS in February of 2010, now 22 years ago, I used this slide, and I actually left it in the old-fashioned format rather than the modern 16:9 aspect. So you can see this is really an old slide. And I got half right, okay? What I said was we need to find the sweet spot where we can have an anti-inflammatory effect without having infections. Well, it turned out that the infections we saw in CANTOS were not opportunistic, just regular standard viral and bacterial infections. And I was worried about impaired tumor surveillance based on the experience with TNF inhibition. But in fact, we saw, as many of you know, a striking in exploratory analyses, a striking anti-cancer effect. So we're still searching for that sweet spot. So I'll have to come back in future years, not the day before the US holiday of Thanksgiving, and share progress with you. And here's the team in my group in times of COVID finishing a big mouse experiment. Thank you so much for your